All right, we're going to look at two related ideas today. First, we're going thing A, we're going to be looking at the harmonic series, which is the sum of the reciprocals of all the positive integers going off forever, and we're going to show that this diverges. In this case, it means it gets bigger and bigger and bigger on up to infinity. And then in the second part of the video, we're going to look at this curve, which is the reciprocal 1 over x. F of x is 1 over x. And we're going to show that the area under this curve from 1 onward gets increasingly larger. So this area is also infinite. Two related ideas that depend on one another. And all of this is a little different. All of this is in my book, SOHCAHTOA, Ravings of a Quarantined Mathematician, which you can get. And there's a chapter in here called Two Concise Proofs of Harmonic Series Divergence. You can get the book. Yeah, you can also read this chapter online. There'll be links for all that below. So let's move on. So first of all, we're going to start with an assumption. We are going to assume that all of this converges to some finite number. And we'll call that number S. And now, if it converges, okay, then the absolute value of each term also converges because they're all positive. So basically, because they're all positive, any sort of convergence will be something that we call absolute convergence. Okay. And because of that, we can split up this series into two chunks. We're allowed to do that. So we're going to split it up into even and odd. And the even part is going to be 1/2 plus 1/4 plus 1/6 plus 1/8 and so on. Okay? And the odd portion is all of the odd reciprocals. So 1 plus 1/3 plus 1/5 plus 1/7, all of this and so on. Okay, so these two should add up. The even plus the odd, that all equals the whole thing. And we can split that up because if this converges, it's absolute convergence because all the terms are positive, so we can split it all up. Okay, right. Now, let's take this odd. Now, we're going to take this original series and we're going to cut it in half. Okay? And when we do that, we end up with 1/2 plus 1/4 plus 1/6 and remember, all of that is 1/2 of the sum of the original series. But hang on, this is the same as the sum of all the even denominator terms. So 1/2 of S equals S even. Hey, but if S even is 1/2 S, then the other half must be S odd because that's all there is. That's all that's left. So S even and S odd are equal. They're both 1/2. Okay, but the plot thickens. Let's compare each term between even and odd, and what happens? Well, 1 is greater than 1/2. We'll put a little sideways greater than sign. And 1/3 is greater than 1/4. Each successive term is greater than the term that we match it with in the even series. So the odd series, if each term is greater than the matched term in the even series, then the odd series must be greater than the even series, or the even series is less than the odd series. So there's our second conclusion. But how can these conclusions both be true? They can't. There must have been something wrong with our original assumption, which is that the series converges. So the series, the harmonic series, does not converge. Since each of the partial sums gets larger and larger and larger, when we say that it doesn't when we say that it diverges, we mean that it goes off to infinity. So this infinity here was correct. And thus we've shown that the harmonic series diverges to infinity. Now we're going to move on to a different issue. So our next task is to take a look at this curve f of x equals 1 over x, this curve right here, okay, and determine the area under the curve between 1 and infinity. Okay. Now, if we were allowed to use calculus, this would be a simple calculation. We would take the integral between 0 and infinity of 1 over x dx, and we would work that out, and we'd get infinity. And so, poof, we would have proven that this area is infinite. But remember, I said no calculus. So what do we have that we can do? We can take our result from our previous adventure and create these areas. This one is 1 over 1, okay? And this one here is 1/2. This one here, 1/3. And I think you see where this is going. These areas correspond to the individual terms of the harmonic series. So all of these areas are going to add up to infinity. And so we can afford to lose this one area, okay? Like, forget it. So just considering from 1 onward, if all of these rectangles underneath the curve, if they sum up to infinity, the area under the curve is larger than that. So it must also, the area under the curve is larger than the area of all of these individual rectangles. So it must also go to infinity. And thus, we've shown the area underneath this 1 over x, between 1 and infinity, we've shown that it is infinite, and we did it without calculus. Bob's your uncle.